All right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Looks like most of us are here, so let's just jump right into it. Here we go. Okay, so let's begin. Make sure that that is turned on. That is important. All right, so let's begin. Text here. Yes. All right, so this was yesterday's lecture, so let's quickly review what we did. We started out by computing the radius of convergence and interval of convergence of power series. And the idea behind this is, for a power series, which is an infinite polynomial, infinite degree polynomial, there's, depending on what the coefficients are, there are power series for which only certain values of x will work. And that would make the series actually make sense. And we know for power series, they kind of always work. They're just three different situations. One situation is the power series will only work for specifically one value of x. That is namely the value it's centered around, so that x equals x naught. So you just get a series of zeros. And that really only ends up being the constant, the C0 term. There's another possibility where there is an interval of x values that will work in the series. May or may not include the endpoints, but if I plug in any x in that interval, the series will make sense. And a third possibility is it will work everywhere for all x's. And so how do we actually go about figuring out where a power series makes sense? Where does it add up to something meaningful, finite, some sort of mathematical object that we can do calculations with? Well, we do the ratio test, always the ratio test. So we do the ratio test. We know for the ratio test to converge, we need the absolute, this L to be less than 1. And that naturally gives us an interval to consider. We always check the endpoints to check whether or not it will work at the endpoints. And that will determine our interval of convergence. Then half the length of that interval is what we call the radius of convergence. That's sort of just like a measure for the span of the x's that will work. So power series are only useful where they work. If you have an object and it doesn't make sense somewhere, you should know not to use it over there. So in this case, this power series works when x is between -1 and 1, which means if there's an x value of 5, let's say, this power series is useless to me. I cannot use this power series when x is 5, but I can use it when x is between -1 and 1. Still a bit tripping in here. And so here we saw that this series was geometric. We actually know exactly what it sums up to. And so we had this idea of this series being equal to this function, like exactly equal, like that's what it is. They are one and the same on this interval. And that kind of brought our attention to this possibility that power series can represent functions. And just knowing this one fact, that this one power series could represent a function, 1 over 1 minus x, we use that fact to figure out how to represent several other functions as power series. For example, 1 over 3 plus x. We also looked at how to represent 1 over 3 plus x all squared. We also looked at how to represent ln of 3 plus x, which, by the way, gave us the fact that the alternating harmonic actually adds up to negative ln of 2, right? So that was pretty cool and maybe surprising. We also saw that the ability to actually represent a function as a power series can get us out of some sticky situations, whether we're human beings or computers. So especially in the case that we've covered, we covered the alternating series approximation theorem, which means when our answer is given as an alternating series, we actually know how to approximate it to within any degree of accuracy we want. And generally speaking, for a computer, it will not be an issue to add up that many values that we would need usually for, 6, 10, 15 decimal places. It's usually not going to be a problem. And so basically we did all that. Everything we did was just based on the fact that we knew this one equation, right? We knew that this one thing was true, that, where is it? That we knew this. And we could do a whole bunch of things just from knowing that. So now the question arose that, what if our function wasn't 1 over 1 minus x, or we can't algebraically manipulate it to look like 1 over 1 minus x? Could we generate a power series from a function from scratch? And the answer was yes. So that method was called Taylor's method, and we can develop what was called a Taylor series, right? So this is just a general method to develop a power series that would correspond to a function. Now, how useful that is something that we'll get into today, because not every time that we do this, the power series will actually represent the function. And there are also functions that don't have power series, but there are cases where this can work and the function will be represented by the power series, and then chef kiss, a lot of nice things happen wherever that happens. So we're going to want to know how to actually generate a power series and when that nice thing happened. And so Taylor's theorem, to do a Taylor series, the assumption is you can always take derivatives of any order, and then you can write the coefficients in terms of the nth derivative of a function. And so we can get this idea. And at this point, this is sort of just a conjecture for us. We're guessing that this will actually describe our function. We'll find out that that's not always the case, but a lot of times it actually is. And the first few examples that we're going to do today, it is the case that they can represent the function, but we'll justify that later. So at the end of the day, these are the formulas we need to have memorized. This is how we generate a Taylor series for a function. It is a series, n goes from 0 to infinity, of f to the nth derivative evaluated at the center point over n factorial times x minus x naught to the n. So our Cn is this guy, right? So this part here is basically our Cn in our power series definition. Now, if we're centered around 0, then our Taylor series would look like this. And in that case, it's called a Maclaurin series. So you'll hear about Taylor series and Maclaurin series. They're really the same thing. The Maclaurin series is just a special case of a Taylor series. When you're centered around the origin, we call it a Maclaurin series, but they're both derived in exactly the same way. It's just that sometimes the Maclaurin series is easy to work with. And if you really wanted it to be centered somewhere else, you can actually shift the Maclaurin series. So we'll actually see some of that. But yeah, and the reason why you might actually care about the general form of the Taylor series is because of what we had earlier. If our interval actually worked like here, we had a very limited interval of -3 to 3. So it turns out sometimes you can do this mathematical trickery where you can move your interval to where you kind of need it by kind of shifting the center. And so, yeah, so we do want to know how to find a Taylor series for a generalized center. But a lot of times for theoretical reasons or just computational reasons, centering around 0 makes things a lot nicer and a lot easier and a lot more straightforward. And we can actually use that in a lot of situations. So the Maclaurin series onto its own is a good thing to know about. All right. Now, I told you what a Taylor series was, but we didn't actually find a Taylor series for anything. So I asked you to try this for next time. Compute the Taylor series for the exponential function. Tell me what its radius and interval of convergence is, which we know we would use the ratio test. Also for the cosine function, also for the sine function. These are some very common and important ones to know about. And that brings us up to today. So we're just going to jump right in and continue. We are going to find the Taylor series. Oh, well, specifically here, I asked for the Maclaurin series. of that. And remember, Maclaurin series just means, if I say Maclaurin series, it just means Taylor series with x naught equals 0. That's all it means. Okay, so the point we're going to evaluate it at is always 0. So remember what Taylor's theorem says. We want, well, that won't necessarily be a part of the thing, but we want the series f to the nth derivative evaluated at 0 divided by n factorial times x to the n, right? Now, x to the n is always going to be the same. N factorial is always going to be the same. The only thing we need to figure out is this part. So that's what we're going to do. So we want from n goes from 0 onwards. The 0th derivative is only the original function. So we're pretty much, we know what that is. So we know that f to the 0 of x is just going to be the original function. That's just, that's just f of x, which in this case is e to the x. And so we want to evaluate f to the 0 at 0, and that would just be 1, right? E to the 0. Okay, cool. Now, what is the first derivative? Well, it's also e to the x. So the first derivative evaluated at 0 is also 1. What about the second derivative? It's also e to the x. So the second derivative evaluated at 0, you guessed it, is 1. I think you kind of see the pattern here. The derivative never changes. The derivative is always equal to the function. And so if you want to look at a pattern, you could guess that the nth derivative evaluated at 0 is always going to be the number 1. And so what you can do is you can go back and plug it into this formula, right? So this would mean Maclaurin series for f of x equals e to the x is, well, it's going to be the series of 1 over n factorial times x to the n, i.e., it's x to the n over n factorial. So that's our answer there. Now, you may have remembered that we actually already looked at this. I do believe it was actually yesterday as well. Yeah, right there. X to the n over n factorial. So it turns out that this guy is the Taylor series for e to the x. I just didn't mention it at the time. And we did use the ratio test on this, and we saw that it converges everywhere. We found the IOC and ROC last class. These were okay. So that is the Maclaurin series for the exponential function, and that one wasn't so bad because the derivative was always the same. Okay. Now, let's actually do the one for cosine. Let's see where we get with that. But we're essentially playing the same game. We know the formula that we want to build up. It's the nth derivative evaluated at 0 We want to figure out a pattern for that we can write in terms of some formula that we can plug into this, the blue formula here at the second line. So we're going to play that game again. We know that f to the 0 of x is cosine of x. This means f to the 0 evaluated at 0 is cosine of 0, which is 1. Okay, cool. F prime of x, that's actually minus sine x. Now f prime evaluated at 0 is minus sine of 0. Now sine of 0 is 0. Oh. It's already shaping up to not be as straightforward as the last one. Let's go again. This is minus cosine x. So the second derivative evaluated at 0 is minus 1. If we can look at the triple derivative, this will be positive sine x. If I plug in 0 into that, I get 0 again. What about the fourth? Well, it's cosine x. And that gives us 1. Now, obviously, this pattern is just going to repeat, right? Because we're right back to where we started. Right, we started with a cosine, we ended up back at a cosine. And so this pattern is going to repeat 1, 0, minus 1, 0, 1, 1, 0, minus 1, 0, 1, 1, 0, minus 1, 0, 1, 1, 0, minus 1, 0, 1. Now, that's going to happen forever. So we kind of want to figure out, like, how would we write this down as a general formula? So one thing you can realize is that we can essentially ignore the zeros. Because if you put in a 0 coefficient in a series, it's like you're plus 0, right? So the idea is, okay, if we can find a pattern for ignoring the zeros, that's good. And here you'd realize that you can ignore the zeros for all odd ends. Right here, you'll notice that here's where n equals 0, here's where n equals 1, here's where n equals 2, here's where n equals 3, here's where n equals 4. Notice that the only time you actually get a non-zero value is when n is an even integer, right? In other words, we can ignore all the odd integers. So note f to the 0, f to the n, f to the n evaluated at 0 equals 0 if n is odd. And f to the n of 0 is plus or minus 1 if n is even. Okay. Now, n is even. You have to remember what the definition of even is. So even means can be written as 2k for some integer k. Whereas odd means can be written as 2k plus 1 or 2k minus 1, depending on what you want to do. But 2k plus 1 is the standard way to look at this for some integer k. Okay. So essentially, what we can do here is we can say for every integer that has the form 2k, it's either going to give me a plus 1 or a minus 1. And you can notice from this pattern that it alternates. It starts with a plus 1, then goes to a minus 1, then goes to a plus 1. We actually have a mechanism for getting that sort of thing. It's the minus 1 to the n. Now, if our n starts at 0, as it does for the series, minus 1 to the 0 will give me a positive 1. And so just minus 1 to the n will actually get this pattern going in the right way. However, then I do want to apply it for only the even powers of x, not the odd powers of x. And so this sort of leads to, so this would mean if I have something like f to the 2k evaluated at 0, that's going to be minus 1 to the k. And if I have f to the 2k plus 1 evaluated at 0, that's going to be 0. Now, again, remember, we have our dummy variables. It doesn't matter if I write them with k or n. Just to fit with the form that we've been using, I'm going to use n. And so that would actually lead me to the form for the cosine. The Maclaurin series for f of x equals cosine x is, well, we have this series, n goes from 0 to infinity. I know it's minus 1 to the n. So that's going to alternate the signs. Otherwise, you're just kind of plugging in 1. It's going to be negative 1 or positive 1, but we don't have to write that 1 here. Just minus 1 to the n will do it. Now, here's where you're going to have to put the trick, because here it's n equals 0 or 2 or 4, which means the coefficient for all the x to the odd powers will be 0, so you don't want to write them. So what you can do here is you actually just write x to an even power. Just double the power of x. And so when n equals 0, you get the x to the 0 term. N equals 1, you get x to 2. N equals 2, you get x to the 4th. N equals 3, you get x to the 6th. N equals 4, you get x to the 8, and so on. So we're only hitting the even ones. Now, of course, the denominator has to match the power, right? It's x to the n over n factorial times the coefficient. So the denominator also has to be only the even factorials, right? So that's our Maclaurin series for cosine. Now, if you were to write this out, this would look like 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial. So you have an alternating sign. It's either a +1 coefficient or a -1 coefficient. These alternate, and they alternate on all the even powers of x. So it's 1x to the 0, -1x to the 2, +1x to the 4th, -1x to the 6th. It follows this pattern that we have here. Right, so that's the Maclaurin series for cosine.
Professor?
Yes.
I tried to write it as, using cosine as the numerator, like to get that same periodic effect, 1, 0, -1, 0. So I had cosine of pi n over 2 over n factorial times x to the n.
Cosine of pi n
over 2.
Over 2. Why would you need that over 2?
Because
I mean,
cosine,
it would, if you replace the -1 to the n with cosine of pi n, that would do it. That would do it automatically.
I didn't want to skip the 90 and 270 degree cosines, the zeros essentially.
Yeah, but the over 2 would put those in, right? Like, it's right. Cosine of pi over 2 would be 0, and cosine of 3 pi over 2 would be 0. Right. Like cosine of n pi is going to be plus or minus 1, right? Mm-hmm. When n is even, it's going to give you a +1. When n is odd, it will give you a -1.
But it doesn't really matter if you include the zeros there, right? I mean, they would just cancel out that term. Yeah, I just tried to match the behavior exactly, like the 1, 0, -1, 0.
So if you write cosine of n pi, right? So when n is 0, that gives you 1. When n is 1, that's cosine of pi, which is -1. When n is 2, you get cosine of 2 pi, which is 1. When n is 3, you get -1. When n is 4, you get +1, right? Like there's no over 2 that's needed because now you're introducing a half.
Okay, and then if you use the 2n, the x to the 2n and 2n factorial, would that be equivalent to this series that we
That
found
is
here?
equivalent. If you write cosine of n pi times x to the 2n over 2n factorial, that's also correct. It's just a very weird way of writing it. Like no one's gonna do that. Like -1 to the n is already a more compressed notation. It's more standard. That will give you all the same values, but like no one writes it like that.
Okay,
It's also kind of poor taste to define something in terms of itself. Like you're saying what a cosine is this thing with a cosine in it. It's kind of weird to think about it that way. So while numerically, mathematically, it will actually work out to be the same, it's actually a very strange way to write it. Most people just write -1 to the n. Right? So technically you will get the same values, but it's a strange way to write it. Traditionally, -1 to the n is how we would do it. Okay. So that's actually the Maclaurin series for cosine. Now we also need to find the radius of convergence and interval of convergence. So let's actually do that. Okay, so again, we use the ratio test. Our L here would be the limit of, now remember, we can ignore the -1 to the n in calculations like this. So I'm just going to put the other parts. So it's x to the 2 times n plus 1 over 2 times n plus 1 factorial times the reciprocal can group these. So this is x to the 2n plus 2 over x to the 2n. Here is 2n factorial over 2n plus 2 factorial. And so we know that this cancels that. This is going to cancel into that, but it's going to cancel, it's going to leave 2n plus 2. Let me bring this in. 2n plus 2, 2n plus 1, and then 2n factorial. And this cancels with that. So we end up with the limit of x squared over 2n plus 2 times 2n plus 1. And the limit is as n is going to infinity. So x is considered a constant here. We're just varying the n. So here we have a fraction where the numerator is a constant and the denominator is going off to infinity. So that limit is 0. 0 is always less than 1. Namely, for all x. Right? For any particular x value that you pick, pi, 14, a billion, doesn't matter. Eventually, the denominator will get bigger than that, and this will go to 0. So this is a situation where that means our interval of convergence is going to be everything. And that, of course, just automatically implies that our radius of convergence is also infinite. So that's that. Any questions? So this is the idea for how to build a power series from scratch using derivatives, right? And doing it this way is saying that we're building a Taylor series. And you want to figure out where the power series works. You always do the ratio test in Cal 2 class. That's all we'll ever use. Now the sine, I'm actually going to skip that because it's super similar to the cosine, right? You're going to have like sine, the zero derivative, plug in zero, you're going to get 0. Then the derivative of sine is cosine, so you're going to get a 1. And then this pattern is going to happen 1, 0, minus 1, 0, 1, 0, minus 1, 0, 1, 0. The same thing is going to happen, is just going to be shifted down 1. You realize that what happens here on the evens, when you do it for sine, it'll happen on the odds. And so you get a very similar thing. It's just that now you have the odd integers instead of the even ones. So this is very similar to f of x equals cosine, except we have non-zero coefficients on the odds. So this one is going to be n goes from 0 to infinity. It's again going to be a minus 1 to the end, but now it's x to the 2n plus 1. So remember, that's how we would get the odds. Notice that when n equals 0, this is 1. N equals 1, we would get 3. N equals 2, we would get 5. N equals 3, we would get 7, etc. You're always getting the odd output from such an expression. And we want the factorial in the denominator to follow that pattern, right? Because the factorial in the denominator follows the pattern of the power of x. And again, in a very similar way, you would see that the IOC is the entire real line, and the ROC is, of course, infinity. So that is for the sine function. Right. The calculations are super similar to the cosine function. You'll just have like one step down. Like for sine, it starts with a 0, then goes 1, 0, minus 1, 0, 1, 0, minus 1, 0. So it just starts one step ahead, which actually makes a lot of sense because you can look at the sine as being like, you know, pi over 2 ahead of the cosine. It's like one step ahead. Yeah, now here is an important thing. This leads to the following table. So these, I actually expect you to know by heart. These are some power series for some very common functions. The 1 over 1 minus x, as you can see there, the Maclaurin series for that is x to the n over n factorial. By the way, we use the geometric series to derive the first formula, but if you weren't through the process that I just told you and found derivatives and plugged in x equals 0, you'd realize that you'd actually get the same things, right? So obviously f of x at 0, you would get 1. Then the derivative of that would just be like 1 over 1 minus x squared. You plug in x equals 0, you get 1 again, and the power of the denominator will go up to a cube, to a fourth. The signs will change, but the derivative by the chain rule is always going to coincide with that negative, killing the negative from the power multiplication. And so you'll always end up with 1. We saw that the radius of convergence for that was 1, and the interval of convergence was minus 1 to 1. E to the x, we just derived this, x to the n over n factorial. It had infinite radius of convergence, and it converged on the entire real line. This was true for cosine and sine. where the cosine is this expression and the sine function is this expression for the Maclaurin series. Now, you can see at the very bottom there, here's something even cooler. For each of the function above, the power series actually converges to the function. Now, that is not something you can take right off the bat, but right now I'm just going to tell you ahead of time that this is true. This is something we're going to discuss later on in general, but it's not automatically true that a function converges, that the power series will converge to the function. But in this case, it is true. And what I mean by that is you can essentially think of these things as equal. In other words, 1 over 1 minus x is this series on that interval. E to the x is this series everywhere. Cosine x is this series. They are one and the same. It's like you're writing something in a different form. It's like someone writes 1/2 and someone writes 0.5. You just wrote down the same thing. You just wrote it with different symbols. One, you wrote it in a decimal form. The other one, you wrote it in a fraction form. This is the same thing. One, we write it in terms of elementary functions, as we call it, right? We learned about the 6 kinds of elementary functions in Calc 1. The other side, you write it as an infinite series. You're actually writing down exactly the same thing. These are one and the same. They're interchangeable. In fact, the higher you go in mathematics, the more you kind of think about these functions in terms of their series, right? Like if you ask someone what a sine function is, they would think it's that series. That's what it is, right? Whereas if you ask like, some high school kid, what is the sine of x? Well, it's the y coordinate on the unit circle when the angle subtended is theta. Sine of theta is the function that gives you that coordinate. Sure, that's true, but that's not how like a math person would think about it. You ask a math person, what is the sine of x? It is this series. That's what it is, right? That is the definition of sine, okay? Now, it is an infinite series, but we're not afraid of that. We know how to add up infinite series. We know this converges. Moreover, we know this converges absolutely. So not only does it add up to something meaningful, but it adds up to something meaningful in such a way that we can do math with it. We can do calculus with it. We can integrate it. We can differentiate it. We can do anything with it that we could do with a regular function. These are one and the same. Anything I can do with the function in the first column, I can do with the function in the second column. These are exactly the same. And in fact, let me show you an example. I'll come back here in a little bit, but let me show you an example. Let me just make some notes here before I run off. So there's, we'll justify later. We'll justify later. And so basically what I'm saying is you can think of these things as equality. 1 over 1 minus x is that guy if your x is between that. E to the x is this guy, well, for all x. Cosine is this guy for all x. Sine of x is this guy for all x. Okay. The problem is for the 1 over 1 minus x, if you start at 0, you can only go as far out to 1, because with 1 you divide by 0, so the party stops, right? And you can only fan out the same distance in both, from the center, you have to fan out the same distance in both directions. So if you can only move 1 unit to the right, it forces you to stop at 1 unit to the left. So this only opens up for a window of length 2. But the others have no such restriction. E to the x is this series in all scenarios, in every situation. Right? And now, here's the thing, and we're going to actually do more of this later. Like, these things are one and the same. Like everything you could do with the function that was on the left, you can do with the function that's on the right. It looks very different, but I want you to understand that they are exactly the same thing. And every manipulation, everything that you would expect from one, you can expect from the other. For example, we know that the derivative of sine x is cosine x, right? We derived that in Calc 1 using the limit definition of a derivative, right? And we had to use one of the special trig limits, limit as x approaches 0 of sine x over x equals 1, and we had to apply that, and we had to do a bunch of stuff. But here's the thing. We could actually derive this directly from the series. So this, if I just literally just replace the sign with the series, look at what's going to happen. Well, I can switch this and I can switch the derivative and the summation sign because we have absolute convergence. So what allows me to do this is absolute convergence. Okay. Now what would happen if I differentiate this? Well, the power rule would apply, right? So everything with an n in there is a constant because I'm doing d dx, the derivative with respect to x. So only x is the variable. So it's just x to some power. So the derivative of that is bring the power down, x subtract 1 from the power. Now, remember that 2n plus 1 factorial is just 2n plus 1 times 2n factorial. So this would cancel into that 2n factorial times. And so I would have minus 1 to the n, x to the 2n over 2n factorial. Look at that. That's cosine. You know, the surprise Pikachu face here, but right. And I didn't have to know some esoteric trig identity, trig limit. I didn't have to remember that the limit as x approaches 0 of sine x over x was 1 for this. It's a polynomial. I know how to take a derivative of a polynomial, power rule. And I could figure out that the derivative of this function is the other function. And you can go the other way. The derivative of cosine is going to be sine. And you can use the series, do term by term differentiation, figure out the derivative of e to the x is e to the x. If I take the derivative of the series x to the n over n factorial, I get back the series x to the n over n factorial. You can actually do this. Right? So yeah, like these guys are their series. They're one and the same. There's no difference between the two. And that's what it's a very important point to actually get. So this is something that you're expected to know like now and forever. Like as long as you're doing math, you're expected to know this. The moment you learn it, you're expected to know it. So I was mentioning before, like there are some things in a traditional Calc 2 syllabus that like I think it's kind of pointless to force you to learn because you kind of never encounter it again. But this is one of those things that you are going to encounter again as long as you're doing math. Like thinking of functions in terms of series is a super duper important idea in math, in physics, in everything that uses math at a higher level than Calc 2. It's one of the things you need to know. It's like inescapable. Like it's like you can't be like going into Calc 3 or higher and like don't know what an integral is. It's that ridiculous to go somewhere and not know what a series is. It's like it's everywhere, right? So if you're using these functions, their series is going to be a useful thing to know about, and they're exactly the same. They're one and the same. Now, these are the ones I expect you to know off the top of your head. So from now on, these are known series. So you know how last time we figured out what the power series of other strange functions were because we knew the power series for this guy? Like I expect you to be able to do the same sort of idea with any of these. And you don't have to justify to me that these series work. I expect you to just know it. Oh, a cosine is this. And anything that has a cosine in it, I can squeeze this series in there and rewrite it as a power series. Like that, I expect you to know. Right? And so, yeah. I also had, so this is just a cautionary tale here, but I've already mentioned this verbally a couple times, that the whole idea of constructing a power series this way works out a lot of the time, but it also doesn't work out all the time. So it's possible to construct a power series that doesn't actually describe the function from which you constructed it. It's also possible that a function would not have a power series. So there are, I guess, three possibilities here. One, you take a function f of x, you create a power series from it, and the power series and that function, same thing. Always give the same values on some interval. You can use them interchangeably, right? And that's what I mean, equal. Literally, you can use them interchangeably. Is there an E here? No. Looks weird. Can use interchangeable, right? You go over your Calc 1 notes, go over your pre-calculus notes. Everywhere you see a sign, write this series instead. Nothing changes. It's like going over your old notes, and every time you see a 1/2, replace it with 0.5. Nothing is going to change. All the answers are going to be the same. All the work that you're doing for the answers is going to be essentially different, essentially the same, except, you know, a proof might actually be easier, right? You need less outside knowledge. We'll actually get into that before. Now, this is not something I expect you to know, or even actually, I'll probably actually never even ask you to do it. But a student in the past asked me, well, what about tangent? You know, you told us about sine and cosine. What about tangent? So tangent is the division of sine and cosine. So you can actually construct that directly from the method I just told you. Or you can actually divide two power series, but that's actually very computationally intensive. So I just put a few links here, just in case you're interested. You can look about, you know, how would you actually derive the power series for a tangent function? It's not something I expect you to know or would ever ask you to know, really. However, anything that you can algebraically mold to look like one of these guys in the first column, I expect you to be able to find a power series for that guy. And anything that is a derivative or integral of one of these guys in the first column, I expect you to be able to find the power series of that guy. If anything is a polynomial times one of these guys, I expect you to be able to find a power series for that guy. We did an example of that like yesterday as well, with that example that Symbol Lab had trouble with. The x over 1 plus x to the 9th. I just thought of it as a polynomial times something that looks like a power series I know, right? So like manipulations like that, you should be able to do. But in terms of using a known power series to develop a new power series, these are the 4 things I'm going to expect you to know. Like you don't have to know a power series for any other random function. You know these 4, you're going to be in good company. And these are the only 4 that I'll expect you to remember. So knowing the power series for like ln of 1 plus x is also sort of useful, or ln 1 minus x, but it's not something that's going to come up for us very often. So, yeah. Yes, and I feel kind of weird to take a break this early, but we're going into a new section. But this is going to be kind of a cool section, I think. Going to talk about some applications of these series that we now know how to find. So for us, by far, the most important application is application 6. Right, it's the most important. Other than that, you should know, well, it's actually involved in this. You should know how to create power series of new functions using the power series of old functions that you already have memorized, like that was in that table that I gave you. So that's already included. But yeah, so the others, it's really interesting stuff and it's nice to know. And conceptually, it can get you through some problems easier, as well as I might ask bonus problems on them. But in terms of like, you know, what you absolutely must know, or, you know, there's going to be very little hope for you, number 6 is going to be the one. That's the one I'm going to test you directly on with more intensity than the others. But I want to go through them because it's actually pretty cool stuff. And it kind of shows you, it gives us an excuse to kind of work with series and get used to them. So it's pretty nice. So we're actually going to look at these these applications, right? So the first one is Euler's equation, right? So for this, I need to remind you some about complex numbers, or I don't even remind you, maybe you haven't even seen complex numbers before, but I'm just gonna tell you like what a complex, remind you about some things about complex numbers and then run with it. So there is this number that we invented at some point called I. It is defined to be something for which its square is -1. In other words, I is like the square root of -1. So there came a point where not being able to state the square root of a negative thing was, you know, it was getting in the way of some good mathematics, right? We had equations that we wanted to be able to solve that we couldn't solve. You know, like x squared plus 1 equals 0. We wanted to be able to get a solution to an equation like that, but with the way we were doing things, we couldn't actually get it done. So it turns out we invented a solution to this equation. We called it I, x equals I, and we just called that the solution. And it turns out that a lot of beautiful math actually happened from that, and a lot of math that we actually needed. So conceptually, when you're thinking about things in the real world, it doesn't actually make sense for this number to be true. But then you found out that it actually does make sense for this function, this number to be true, because physics uses it all the time, and we cannot describe physical reality without the existence of such a number. So it turns out that on one sense, like I square something and it's negative, doesn't make any sense, depending on, you know, for all these years of math, everyone was telling you, oh, something squared is always greater than or equal to 0. You know, you get to a point where now we're like, let's expand that a little bit. And let's pretend that there is a number for which this is true. And it turns out we needed that to have a full description of reality. Yeah, so I remember there was a point when I was very young where I was always told you couldn't subtract a larger number from a smaller number, you know, like, so if you have 5 toy trucks on the table, you can take away 3, you can take away 4, you can take away 5 of those trucks, but you can't have 5 trucks on the table and take away 6. And then they told me about negative numbers, and I was like, man, these people lied to me. Like, you mean I can take away more toy trucks than were actually there? Now, in physical reality, it doesn't seem to make sense, but the idea of a negative number is super important, obviously. And so, yeah, so just take it on faith right now that such a number exists, a number that when I square it, the result is -1. And by repeated multiplication, you can find the following, right? So I is the square root of -1. So if I multiply by I times I is I squared, that would be -1. Multiply by I again, I cubed would be -I. Multiply by I again, I to the 4th would actually be +1, because I to the 4th is like I squared times I squared. -1 times -1 gives us +1. I to the 5th. And you kind of see that this repeats. Okay. So now that's actually not, just knowing that is enough for what we're going to do, because I'm actually going to want to derive a very important equation. And right now, that's all we need to know about complex numbers to derive that equation. So it turns out that a number that comes up very often is this number, e to the ix, right? X is a real number, right? So it's e to what we call an imaginary number, okay? Now, we're actually going to do something with this and figure out what this thing is. So here we go. So if I have e to the x, we know, well, now we know e to the x is this series. That's what it is. What that means is anything I can do to e to the x, I can do with this series. It also means, therefore, that if I were to replace x with ix, I can go into this series and replace x with ix. So if you just do that. So this means that e to the ix is just going to be the series of I to the n, x to the n over n factorial. Okay, now what can we do with that? Well, let's write out a few terms. Now, if n equals 0, well, let me just write out without plugging anything in really, except for the n's. So obviously if n is 0, I just get 1. If n is 1, I would get ix over 1 factorial. If n is 2, I would get I squared x squared over 2 factorial. N is 3, I cubed x cubed over 3 factorial. N is 4, I to the 4th x to the 4th over 4 factorial. I to the 5th x to the 5th over 5 factorial. So on. Now, I'm going to actually apply this set of equations that we have here. So it's 1 plus ix. Now, what is I squared? I squared is actually minus 1, right? So I can replace this with minus 1 x squared over 2 factorial. What is I cubed? I cubed is actually minus I. So this is just minus I x cubed over 3 factorial. What is I to the 4th? I to the 4th was positive 1. Right? What is I to the 5th? Well, it's I to the 5th is I. And then the pattern essentially repeats here, right? So we're going to have that. Now what we can do is we can actually group the guys with i's in it and group the guys without i's in it. So we're going to group all the guys with i's and without. So it's I times all of these guys. Now, who has the i's? Or let's start with who doesn't have the i's. Well, notice that all the guys who doesn't have the i's are all the even powers, right? The x to the 0, the x squared, the x to the 4th, the x to the 6th, they don't have it, right? So this would be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. Turns out the next one would be minus x to the 6th over 6 factorial. Because I to the 6th, right, is going to be like I squared cubed. I squared is negative 1. Negative 1 cubed is negative 1. That continues. Go on what the odds, that's x minus x cubed over 3 factorial. It should be a plus. Plus x to the 5th over 5 factorial. Minus, the next one would be x to the 7 over 7 factorial. You can follow the pattern. Now, what do we notice about this guy? Do we notice that guy? Do we know that? What is that? Does anyone see what that is? Turns out that that's cosine. Turns out that this guy is sine, right? That's the first one is x to the 2n over 2n factorial. The last one is x to the 2n plus 1 over n 2n plus 1 factorial. So this is equal to cosine x plus I sine x. And that is what this guy is. Now this guy actually has a name. It's called Euler's equation. Right? Now, because we're using cosine and sine, a lot of times people write this in terms of angles like theta instead of x, but it's the same equation. You would derive it the same way. But yeah, e to the ix is this. And that is actually a super important equation. So when you go to, like, if any of you take complex analysis at any point in the future, or you do any physics at any point in the future, even if you're doing differential equations, like it's very important. It shows up all over the place. Any engineering that deals with enough physics, or any physics class or any math class above this level, that's going to be an important thing to know. It's called Euler's equation. Now, here's something really interesting about Euler's equation. What would happen if you plug in theta equals pi? So this would actually give you e to the I pi. That would be cosine of pi plus I times sine of pi. Now, sine of pi is 0. Cosine of pi is -1. So you would get e to the I pi equals -1. Or in other words, you would get e to the I pi plus 1 equals 0, which is a very interesting equation. It actually has a name. This leads to what is called Euler's identity. And it is considered by many people to be the most beautiful equation in all of mathematics. It has all the important constants: e, I, pi, 1, 0. You can build so many things from these numbers, right? Like e to the x is the most important function in mathematics. A lot of people also believe that. You can build up everything, all of calculus, you can build essentially from exponential functions. To prove even something like the power rule in most generality uses exponential functions. And so the exponential function, very important function. You plug in I times pi. I allows us to now solve any polynomial equation, and we'll always have n roots up to multiplicity. Pi comes from very natural ways, including just analyzing the circle. 1 is the multiplicative identity for the real numbers. 0 is the additive identity for the real numbers. Addition and equality, very important math operations. You also have multiplication, exponential. This one equation has the 4 basic mathematical operations, has equality, has all the important constants, all in one very short equation. Beautiful. And so a lot of people like that. I wrote a little blurb about it because it's a very nice thing to know about. So that's one thing. And this is used all over the place. In fact, we're going to use it a little bit later to derive some other stuff to show you that's pretty cool. But this is like one application of just knowing a power series. From a power series, you can easily derive nice little equations like that once you can recognize the standard power series for certain functions. And we'll actually look at some later on. Next, we're actually going to learn something pretty cool. We're finally going to learn how to expand a radical. So first day of class, I mentioned that, you know, if you want to expand the radical of 1 plus x squared, a lot of students erroneously write this as 1 plus x by distributing the radical across the sum. Very illegal. We call it a blasphemy. Doesn't happen. So you might ask, is it possible to expand a radical like that? And the answer is yes. However, you will need an infinite number of terms. And with series, I'm going to actually show you how to actually get that after the break. So stay tuned. So we're going to take a 5-minute break right now. And when we come back, we will continue. Okay, and we're back. And we see, Euler's equation, Euler's identity. Very beautiful equation. Let's move on. Let's talk about the generalized binomial theorem. Now, I don't know if any of you have learned this specifically, but this is something that you should have learned a long time ago. Maybe it was expressed differently. Now we have a different language for it with factorials and stuff. So there's something called the binomial theorem. And it tells you how to actually expand the sum of two things raised to a positive integer power. And it's actually a formula for a finite series, actually. So it tells you that you can actually expand things in this way. So Maybe I'll write this here. What this basically is saying is that x plus y to the n is going to be equal to n choose 0. Well, I can actually do this either way, but whatever. N to the x to the n, y to the n, x to the n minus 0, y to the 0, plus n choose 1, x to the n minus 1, y to the 1, plus n choose 2, x to the n minus 2, y to the 2, plus da da da. Going all the way down to n choose n minus 1, x to the 1, y to the n minus 1, plus n choose n, x to the 0, y to the n. And actually gave you a formula for actually writing that out. So for example, I did think to write it here. This is actually the same as writing 4 choose 0, x to the 4th, plus 4 choose 1, x cubed y, plus 4 choose 2, x squared y squared, plus 4 choose 3, x cubed y, xy cubed, plus 4 choose 4, y to the 4th. Turns out that this number is 1, this number is 4, this number is 6, this number is 4, and this number is 1. And that actually gives you the coefficients in the expansion. Another way you might have seen these come from is Pascal's triangle, where you start with like this triangle of 1s. And then you start the list with 1, and to get each new number, you add the 2 above. 1 plus 1 gives you 2. 1 plus 2 gives you 3. 1 plus 2 gives you 3. 1 plus 3 gives you 4. 3 plus 3 gives you 6. 3 plus 1 gives you 4. And you can kind of continue with this pattern. And at any line, it actually gives you the coefficients for expansion of the power at that line, coefficients of 4th power expansion. Right, so that 1, 4, 6, 4, 1 is the same numbers that show up in the expansion of x plus y to the 4th. Turns out, like I said, you can actually write this as a series, a finite series, and write the coefficients in terms of factorials. And that pattern actually tells you how to actually write those out. So maybe you've seen this before in pre-calc, yeah, there's a general way to actually write out a multiplication of 2 terms raised to a positive integer power. It's called the Binomial Theorem. So it gives you a general formula for doing this. So we know how to do this very well. So here's the thing. It turns out that this theorem still holds if you pretend n is not an integer. And it also still holds if you pretend it's not a finite series. So the idea is, when you learn about the gamma function and blah, 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 you're going to realize that, okay, if n is not an integer, we have to think of this as an infinite series. And it turns out that leads us to something like this. Right? So this is like for n not an integer. For example, you can plug in n equals 1/2 into this formula. And you want to actually follow this definition, the definition in the green box, to find the coefficients, and it will actually work. So for example, if I plug in x plus y to the 1/2, which I know is the square root of x plus y, I can actually think about it as this series. Now, what that would look like is, you know, 1/2 choose 0, x to the 0, y to the 1/2 minus 0, plus 1/2 choose 1, x to the 1, y to the 1/2 minus 1, plus 1/2 choose 2, x to the 2, y to the 1/2 minus 2, and it would keep going. Now, based on that formula, a half choose 0 is going to be 1, y to the 1/2. Half choose 1, we're going to use this formula because that's what this symbol means. It's called n choose k, because it has an interpretation in combinatorics. You'd see this in a probability or statistics class or a combinatorics class. It's the number of ways you can choose k objects from n objects. So it's a mathematical counting formula, but it actually shows up here also. So if I apply that formula as it is, I pretty much start at a half. So then it's going to be a half. It would just actually be a half because on the bottom, it's going to be 1 factorial. Then it's going to be a half times a half minus 1 over 2 factorial. Then it's going to be a half times a half minus 1 times a half minus 2 over 2 factorial. So it's a half minus 0, a half minus 1, a half minus 2. Okay, right. And this pattern actually repeats. And if you continue, these are the coefficients you'll get. So if you actually start calculating all those fractions that I just wrote down, right? So it turns out that this is going to be a pattern that you would get by the radical. Well, here I replace the x with 1. I replace the y with 1. And technically I replace the x with 1 and the y with x. But these would be the numbers. If you work out these coefficients, that's what you're going to get. The first one is a 1. Then this coefficient here is going, it's on the eraser. This coefficient here is a half. This coefficient here is an 1/8. This coefficient here is going to be a 16th, and so on. Right. So the idea is, if you apply these formulas, which, it's in the notes, so you can look them up. I don't really necessarily need to memorize these at the moment, but you can get these coefficients. Now, because this is a series, it actually converges. I could replace, for example, my x with x squared, for example. And then I would have this expression. The radical of 1 plus x squared is actually this infinite series, and it goes on forever, right? So it's actually 1 plus x squared over 2 minus x squared over x to the 4th over 8 plus x to the 6th over 16, and so on. And this will actually continue forever. It will actually never terminate. But you can expand the binomial theorem in this way. You can write it as an infinite series whenever your highest power is not an integer. It turns out it will never settle anywhere. When your n is an integer, the factorial function just gives you zeros everywhere except on the positive integers, and it's kind of above our pay grade. But for now, just realize that the formula can be extended this way. And you would realize how far off you would be if you were to think that this is the case. You're missing like an infinite number of terms. And you're not even at the, you're not even correct to 2 terms. Like, you're immediately wrong since the second thing you write down. Like, that's not even an x here. Like, there's no x. Like, you're assuming that this thing is linear, and it's very not linear. Even when reduced to like 2 things, this function actually behaves more like a quadratic when limited to two terms than it does a linear term. So like, this is just wrong all over. Like, there's nothing right about this. And yeah, I mean, if you don't believe me, you can actually plot this, which is something I'd recommend you try for your own amusement. Graph the graph for 1 plus x squared with a computer. You don't have to do this by hand. And then slowly graph the graph for 1 plus x squared over 2. And you'll see that it kind of fits it, but it might deviate somewhere. But then when you add another term, it fits it even better. 1 plus x squared over 2 minus x 4th over 8th. And you'll see it fits it a little better. then add another term, 1 plus x squared over 2 minus x to the 4th over 8 plus x to the 6th over 16. It'll fit it even better. And you'll see that, oh, these are actually the same. As I move further in the series, it starts to fit this function. We're going to actually talk about that idea later, but yeah. So I mentioned that. That's something to try. Just either actually graph this on your computer and actually see. You'll visually see that the right side is becoming the left side the more terms you get. And we're actually going to visually see that ourselves a little bit later. But let's move on for now. So that's another application of series. We can now expand radicals of sums, which is pretty cool. Here is another application. We can actually use series to help us compute limits. So if you look at this limit here, give this to the average Calc 1 student, and they're going to be like, okay, I can just use L'Hopital's rule 3 times and do it, which is true. You can, right? But I didn't want to get too crazy with this crazy example, which you can't really verify some other way. So yeah, I encourage you as the reader to try your hand at this and convince yourself that the answer that I'm going to get with series will be the same answer that you would get by traditional means, like L'Hopital's rule. Apply L'Hopital's rule 3 times, you can get to this answer. But I can apply series once and get to that answer right away. So we now know that the sine function can be written as a series, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. Right? Minus x all over x cubed. Okay. So I know that that's my sine function. Well, now we know, right? We derived that earlier today, right? And you should know how to do. So the cosine is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. The sine starts with x, and then it's all odd powers over the same factorial, alternating sign. But here you can quickly see that your x kills the x, and dividing the x cubed into everyone on top, you would end up with minus 1 over 3 factorial plus x squared over 5 factorial, x to the 4th over 7 factorial, x to the 6th over 9 factorial, etc. These actually don't even matter because your x is going to 0. So all of these terms go away. And what are you left with? Minus 1 over 3 factorial, which we know is 1/6. The answer is actually minus 1/6. Now you can actually apply calculus and use L'Hopital's rule 3 times in a row, and you would actually eventually get to minus 1/6. It wouldn't take you much longer than this, but I don't want to give you a super crazy example. That's going to take forever for you to actually verify it. But yeah, you can practice. You should know how to use L'Hopital's rule to evaluate a limit anyway. It's a good time to practice and try to see that you would eventually get this answer with L'Hopital's rule 3 times in a row. So yeah, so you can actually find limits a lot easier, and now you won't need calculus. You won't need some sort of sophisticated method. You won't need to apply some method multiple times over. You can get to an answer right away using series, because the sine is that series. Everywhere you see a sine, you can use that series instead, and you're good. By the way, it's another reason you can also see this. I didn't plan on doing this, but it just occurred to me. X approaches 0 of sine x over x, right? Another way to actually know that, derive that, is to realize that this is just the limit as x approaches 0 of x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus da da da, all over x. Divide x into everyone, that's 1. X squared over 3 factorial plus x to the 4 over 5 factorial. And clearly now, if you plug in 0 everywhere, look at that. You rederive the fact that that's 1. Right? So series right? Now, by the way, like to get to a point where you could use L'Hopital's rule to do that, you had to learn calculus, right? Like about derivatives, and you had to learn L'Hopital's rule and all that stuff. The actual proof of this, when you saw it in Calc 1 the first time, was this geometrical proof where they sketched a circle and they drew this triangle and another triangle inside of that triangle. They create similar triangles, and they did all this rigmarole with SOHCAHTOA, and they're like, well, this has to be approximately that, and then we can take the limit. And they had this, it was a very convoluted argument. And it's like, L'Hopital's rule is an easy argument, but hey, series is just as an easy argument. You can see here, like you can do that proof in essentially a single line and figure that out again. So yeah, that's another use of series. I actually left some for you to try just for fun. Just for fun. Yeah, so try these. Might ask as a bonus or something. So try your hand using series to evaluate those. And I guess you could also try using L'Hopital's rule if you want to try that, and you can actually compare the two. Sometimes it's actually going to be annoying. Like in that first one, L'Hopital's rule, you'd have to apply it like a couple times, and in the numerator, you'd have to apply the product rule a couple times to like two different functions. So it's kind of annoying to apply. But if you have write it as a series, it's actually not that bad. Okay, so that's another thing you can do with series. You can use it to compute limits. Also rederive formulas, which is something else we're going to talk about in a little bit. And I'm rushing through these applications because, like I said, they're good to know, but the one I really want to focus on is application number 6. These other ones, if something I said went over your head or you missed it, it's kind of okay. Go back and read it in the notes, and it'll be fine. What we really want to focus on is application number 6. So I'm just kind of rushing through these. But here's another application of series. Being able to write constants as infinite sums, which, again, it might look like a party trick when you write it. It's just like, ooh, you can do this. But it actually does help certain applications sometimes to be able to do this. And a computer, for example, if you program your computer to know this, it can figure out a lot of things much easier than it would be able to otherwise. So I'm going to do a couple examples here. And one of them is actually going to be, part B is going to be a very good example to know because it's also leading into example 6, the application type of 6. And so, but for E, I'm just going to do this one. For example, I could write E as an infinite sum, right? Like if I have the number E, which I know is the limit as n approaches infinity of 1 plus 1 over n to the nth power, that's a limit. It's a very weird thing. Another way to express it is as, this non-repeating infinite decimal, 2.71828, blah, blah, blah. But here, what if I wanted to express it as an infinite sum of terms? I could do that with series, and it's actually not that hard here. So I know that e to the x is equal to this. So this must mean that e, which is just e to the 1 power, must be equal to 1 over n factorial. This means that I can write e as 1 over 0 factorial plus 1 over 2 factorial. Well, 1 over 1 factorial. Plus 1 over 2 factorial, plus 1 over 3 factorial, plus 1 over 4 factorial, going on forever. That will actually add up to the number e. You can also realize, which is a nice thing, someone who wanted to approximate e, like, let's say someone didn't know e was 2.7 blah, 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 or 2 point something, but they didn't know they didn't know this definition. Like figuring out what e is as a decimal approximation using the limit formula very computationally intensive. But writing it as an infinite sum, you can actually see that right away, because right here, this is already 2. And right here, this is like something, right? Like we don't know exactly what it is, but I can clearly see that E is 2 plus something. That something I know is less than 1. Because we saw that a half plus a third plus a fourth plus a fifth was 1. Here, the denominators get larger by a lot. So I can know that E is 2 and change, right? Just by looking at the series. Right? I can know approximately what value it is, and that is a useful thing to do. So if you can write some number as an infinite series, sometimes even the number might look complicated. Like to define E, like that technically speaking is a limit as n approaches infinity of 1 plus 1 over n to the n. Like that's like, if I tell someone that, like, I don't know what that number is. Is it 5? Is it 17? I don't know. But I write it as a series. Oh, it's 2 point something, right? Like it's clear like what it is. You can do a comparison a lot easier. So that's another thing that you can do with series. Just write these infinite constants and constants as an infinite series. And this might be useful in some contexts because the number itself might have a very complicated description. And you might think that writing it as an infinite sum is also complicated, maybe even more complicated, but there are some contexts in which it's less complicated. Like here, I could eyeball the right side and know roughly what E is, whereas I can't do that with the left side. Like if you tell me the definition of E as a limit, I'm not going to eyeball that and know, oh, that's going to be 2 plus something. So there's that. Now, B kind of leads you into being able to write something, an important mathematical constant as an infinite sum. But it asks me to start by finding a Maclaurin series for the arctangent. Now, what I'm going to do here is I'm not going to actually go through the usual way of finding derivatives. I'm actually going to use a known power series, which we can do at this point. So we'll use the fact, this is part 1. We'll use the fact that arctan is this integral. All right. So we have this integral. I can write it as 1 minus a minus x squared. And I can use a power series to describe something like that. This is just the power series of that thing to the nth power. Now, this is absolutely convergent. So I can switch the series and the integral sign. And this is going to be minus 1 to the n, x to the 2n plus 1 divided by 2n plus 1. Right? Now, of course, that's going to be plus c, which I have to find. But I know that this should give me like an arctan on this side, plus a constant. I can move the constant to one side. And so I can say, just plug in a convenient value for x. If x equals 0, we would actually get arctan of 0 equals the series of 0 plus c. This means, of course, here c equals 0. So I can kind of ignore it. And so essentially, our arctangent is this series. Okay, so that series is the arctangent, right? And I could do that by using a known power series. And notice that is the integral of this. It looks like 1 over 1 minus x, which I know is the series of x to the n. So instead of my x here, I have minus x squared. I can actually plug this in and derive a series for this guy. Sure, I could use a formula to make this look like x to an integer power, like set 2n plus 1 equals k, and then it will look like x to the k over some complicated formula. But I don't want to actually do that. This is actually good enough. So part 2 actually says, evaluate the above at x equals 1. So that's what I'm going to do. So for part 2, if I set x equals 1, this means I have the series of minus 1 to the n over 2n plus 1. Now, what does the left side give me? What is arctan of 1? Anyone? That's actually pi over 4. Now, if I start writing out what this series on the right is, it's just an alternating sign of fractions where the numerator is always 1, but switches alternating sign. The denominator is actually just odd integers. So this is going to be 1 minus a third plus a fifth minus a seventh plus a ninth, like that. So this is actually going to be, this means pi, our very famous number, which a lot of people just always automatically associate with a circle, which, I mean, in higher mathematics, it's actually not, it's not the best interpretation for pi, but a lot of people think of it that way, is actually 4 minus 4 thirds plus 4 fifths minus 4 sevenths plus 4 ninths. Like that. In fact, you'd realize that this negative, the negative that follows is always larger than the following negative. So this kind of tells you that it's 4 minus something. So you can kind of see from this series that your pi is going to be 3 point something, right? So this is obviously 4, and this is something negative. So pi is roughly 3 point something. So you can actually figure that out. Yeah, so that is interesting application. That was the 4th application. So writing constants as infinite series can be useful. We'll get back to more applications like this pretty soon. It's the one I want you guys to focus on more mostly. Here's another one. We touched on this earlier. We could derive identities. Like, for example, I re-derived the fact that the derivative of sine x is cosine x. I re-derived the fact that the limit as x approaches 0 of sine x over x is 1. I can do a lot of things. And so here I can actually derive some things about our hyperbolic trig functions, right? So remember our hyperbolic trig functions, we could define them in terms of exponentials. And now we actually know how to write exponentials in terms of series. And so I can use this to figure out the actual series representation of a hyperbolic cosine, for example. And you're going to see something very interesting. So remember, cosine and the hyperbolic cosine, they were developed in a similar fashion, right? So cosine gave you the x coordinate in the equation x squared plus y squared equals 1 as you traverse counterclockwise. Hyperbolic cosine, or cosh, gave you the x coordinate for x squared minus y squared equals 1, right? So they had a very similar genesis. It's a matter of a change of sign. And you're actually going to realize that this actually has implication for the series itself. And you're going to realize that hyperbolic cosine is actually a pretty good description of this function. So for example, this is just 1/2 times, of course, e to the x plus e to the minus x. And I know that e to the x as a series is x to the n over n factorial. Now, minus e to the x as a series is minus x to the n over n factorial. Now, what I'm going to do is I can write out some of these guys. Let me put this in. So the first one is going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x fourth over 4 factorial plus da da da. You know, this is going to be plus this one, because it's a minus 1 to the n, it's going to be negative on all odd n values. So it's going to be 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4th over 4 factorial minus x to the 5th over 5 factorial plus da da da. Now, what you realize here is that the x would kill the x, the cube would kill the cube, this would kill that. All the odd ones would actually cancel each other out. And all the even ones will actually double up. You'll have 1 plus a 1 and this plus that. All the even ones will actually double up. And so you can double the 1 plus the x squared over 2 factorial plus the x to the 4th over 4 factorial plus the x to the 6 over 6 factorial. Now the 2 would cancel the 2. And when you write this as a series, you realize the form that it looks like. It looks like x to the 2n over 2n factorial, which looks a lot like our cosine. The only difference is there's no alternating sign. It's hyperbolic. So it's like a cosine, but it's better than cosine, or, you know, so it's like a cosine. But no alternating sign. Yeah. Right. So yeah, calling it a hyperbolic cosine is actually a very good name. Like even the series, they look almost the same. And so this is something that shows up all the time. There was a point when I was teaching differential equations and we saw like this series popped up out of somewhere where it's like, oh yeah, that actually makes a lot of sense. Like we were looking at this physical system and this series popped up and we're like, oh, that's a hyperbolic cosine. And that makes a lot of sense that it's a hyperbolic cosine. So it's a very interesting thing. So knowing the series for it was actually very useful. And in fact, you could derive that in general. You'll notice that the hyperbolic sine also looks very similar to a regular sine, except there's no alternating sign. The tangent and the other guys would actually be similar. So yeah, so if you know the series for the regular trig functions, the series for these guys actually fall in line pretty easily, which then makes you realize that, oh, they were very aptly named. So you can figure out that stuff from series without going through this idea of playing the derivatives game. So series sometimes help you find other series which are useful for other applications, and that's pretty cool. So you can derive other series. And I actually want to derive another formula for you. Let's derive a trig identity. And again, this is another one where the derivation for this, if you go back to pre-calc where this was derived for you, you'd realize it was a very convoluted derivation. And it was like a rectangle with a right triangle inside of it at an angle. And then there was another right triangle stacked on top of that one. And the acute angle, the angles at the bottom right corner, one was called A, one was called B, and they used that and they measured it was very convoluted. I actually did the proof for my pre-calc class. People's eyes were glazing over, and yeah, it's very messy. But I'm actually going to derive that same formula using Euler's identity, which again we know by series, or Euler's equation, and it's going to be pretty cool. So so we can actually get away with not being that great with our geometry by using this. For example, we know that this would be equal to this just by laws of exponents, right? You add the powers, multiply things of the same base, you add the powers. Now you apply Euler's equation. This one, you know, is cosine of A plus I times sine of A. This one here is going to be cosine of B plus I times sine of B. How do I know that? Series. Okay, so now I'm going to start multiplying out. So this is going to be, take the cosine A, multiply everybody in the second one. So cosine A, cosine B plus I cosine A sine B plus take this I sine A, multiply everyone in the second parentheses, sine A cosine B plus I squared sine A sine B. Now, of course, I squared, that's -1. So what I'm going to do is I'm going to group the guys without the i's. So that's cosine A cosine B minus sine A sine B. Put the i's over here. That's going to be cosine A sine B plus sine A cosine B. However, also by Euler's identity, I know that this by Euler's equation. So Euler's equation would tell us these are that, again, Euler's equation. But Euler's equation would also tell me that this guy is equal to cosine of A plus B plus I times sine of A plus B. And look at what we just did. We just derived the addition formulas for sine and cosine. That is this. And that is that. So through some very simple calculations, which we know from Euler's equation, which we know by series, we can actually figure out some addition formula trig identities, which is very, very cool. I actually put the derivation from basic principles, and you'd realize, even as Calc 2 students, it might even take you a while to wrap your head around this. You'd probably have to pause the video a couple of times to see, wait, what did he just say? Because yeah, so the video's there. You start at 25:18. You'll see me actually derive the addition formulas using geometry. That technically is at the pre-calc level, but trust me, it was way more complicated than this. This gave us a short formula. And you could go through and you derive all sorts of stuff. You can derive the product of some formulas using this. You can derive all sorts of things using this. So that's nice. So here's the important application. Okay, so all the other ones were pretty cool. Just thought I'd show you a lot of things in math can be reinterpreted in terms of series, and you can actually get a lot of mileage out of that. And even some of the problems that we would be doing, like having to take limits and stuff, you can rewrite those in terms of series and interpret a lot of things from that, derive a lot of identities and stuff. But this is the thing I'd test you directly on, okay? And we're going to do some things that heretofore, I kind of told you were impossible, but now the impossible is going to become possible using series. Well, not exactly. So I mentioned before that if you wanted to integrate something like, sine of 2x squared, this was impossible. It was impossible in the sense that there is no way to express this in terms of elementary functions in a simple way, in the sense that all the functions you learned about up until this point in your life, there's no combination of those functions via multiplication, division, addition, subtraction, exponentiation, or radicalization, for which you could say, I can construct this function, and if I take its derivative, it will be sine of 2x squared. There is no such function. You cannot write down such a function. It turns out, though, that to say the derivative, the antiderivative is like impossible to get isn't exactly correct. It turns out we can get it in terms of a series. But this is not an elementary form, or this is not what we would call a closed form, which usually when people say something is possible to express an answer, they mean it in that way. Like, I don't need an infinite number of terms to write it down. I can write it down in a very concise way using a finite number of functions that are familiar to everybody, right? So that's what we mean when we say, oh, we can find the answer in terms of elementary functions. So it turns out that we cannot integrate this function in terms of elementary functions, but we can integrate it in terms of series. And that will actually allow us to find, integrals that we wouldn't be able to find before. And so that is a very important application for us. So I want to actually do that now. In fact, we're almost on the hour. We're about 5 minutes from the hour. So I'll actually take a break here because I want you guys kind of fresh for this. So we'll take a 5-minute break right now, and then we'll actually get into this application. This is the one I want you guys to really pay attention to. And stop me if you have questions. So we'll pause here for a little bit. All right, let's get to it. Let's actually do this application, important one. So you'll see problems like this on a test, or problems where you'd have to know how to do something like this for a test. So perk up, make sure we understand this. We've actually done this sort of thing a few times already, but now I want it all in like one problem formally, and just try to get everything done all in one shot, so we can tie a few ideas together and get to a complete understanding of how you'd attack a problem like this. So ultimately, it's like we want to approximate a definite integral for a function that we don't know how to integrate, is essentially it. And we sort of want to know how good our approximation is at the same time, okay? So it starts out, and A might not be something that I ask you to explicitly do, but the moment that you see an integral like is expressed in part B, you would kind of know that, hey, that's impossible to integrate. So I would probably need series here. But that's what we're going to do. We're going to start out with finding the Maclaurin series for sine of 2x squared, which is actually not going to be that bad because it's a sine function. So there are times when I can find a series for something based on an integral relationship. So we did that, or a derivative relationship. But there are other times where we can literally use a known power series to find another one. We've done examples of all this before, but we're going to do it again here. So let's actually look at part A. Right. So what is a Maclaurin series for the sine of 2x squared? Well, we know that the sine of x is equal to minus 1 to the n x to the 2n plus 1 over 2n plus 1 factorial. Parenthesis looks weird. Right? And this is true for all x, right? So in particular, this would mean that if I have sine of 2x squared, that would work. That's another real valued. So I can actually just plug this in for x in our series. Minus 1 to the n. And here I'd put in 2x squared for x. Right. So now at this point, I'm going to just kind of clean this up a little bit. Because I can see in the future parts of this problem, I'm going to need to do some calculations. So I might want to look at this in a different way. So I know that's going to cause an alternating sign. This will be 2 to the 2n plus 1. So it's always going to be 2 to an odd power. And then this is going to be x to a 4n plus 2. So the x is actually always going to have an even power here. And this is over 2n plus 1 factorial. And so, I mean, I don't think we can clean it up any more than that. So 2x squared is this. And I already know it has an infinite radius of convergence and all that. This will also work for all x. And that's part A. Just use the fact that we know what sine is as a power series and just replace the x with the thing. So it's kind of like a substitution, but you don't need the dx to work out. Right? You can just literally just do a substitution. That's the new function you're doing now. And now, if I want to integrate the sine of 2x squared, it's the same as me integrating that series. That series is sine of 2x squared. They're one and the same. There's no difference between the two. The series on the right converges to that function. So that leads us to B. Now for B, we want to estimate this integral using 3 fractions. Well, I think I reduced this to 2 fractions. I don't know why it says 3. Oh, I think there's something going on online. I don't want to mess with it right now. So I couldn't bother with 3 because ultimately I'm going to have to do 4 and I got tired. So let's write this as 2. Okay, so let's continue. So we're going to write this integral. We want to express it as the sum of 2 fractions. All right, so here we go. So I know then that the integral from 0 to 1/10 of the sine of 2x squared, well, that's just going to be the integral from 0 to 1/10 of this series. Dx. And so now because of absolute convergence, we know that this guy converges absolutely to the sine of 2x squared for all real x. This will then therefore in fact be true on the interval of 0 to 1/10. And so what that means is I can switch the series and the integral. Now, at this point, this looks very messy, but just remember, the integral is with respect to x. So this whole thing, that's just a constant. The only thing you're really worried about is x to this power, right? So it looks messy, but it's just looks, right? We don't discriminate based on looks, right? That's just a constant. So the integral is actually just going to be, it's the same constant here. But we're going to add 1 to the power and then divide by the new power. This is between 0 and 1/10. Fundamental theorem of calculus. So now I'm going to plug in 1/10. Obviously, if I plug in 0 for x, I just get 0 everywhere because I get 0 in the numerator. So the only thing I have to worry about is plugging in the 1/10. And so that x to the 4n plus 3 is going to move to the bottom as 10 raised to the 4n plus 3. So this is going to look like minus 1 to the n, 2 to the 2n plus 1 over 2n plus 1 factorial, 10 to the 4n plus 3 times 4n plus 3. And that is actually the answer, right? So that is the integral of this series on that interval. And by the way, this is the antiderivative, right? Before I actually plug that in. But, well, the series of that is the antiderivative, right? Right, but that's like an infinite way to write down. Like you need an infinite number of terms to write this down. So it's not exactly something that a Calc 1 student would be able to write down, for example. So it's not in terms of elementary functions. But that would be the antiderivative. And what you're looking at here is the definite integral. This will add up to the value of that integral, right? So if I want to find the area under the curve y equals sine of 2x squared on the interval 0 to 1/10, that series is the answer. Now, let's just follow with the question. We'll actually follow up with getting close to the answer before. It says we want to approximate this using a sum of 2 fractions. What I'm going to do, though, is I'm going to calculate 3 fractions because we're going to need to use it ahead later on. So obviously, I'm going to plug in n equals 0. Right? What happens if n equals 0? I would get just 2 to the first power divided by 1 factorial, 10 cubed times 3 plus, well, in this case, it's a minus 1 to the n, so that's actually going to be a minus. Now I'm going to plug in n equals 1. So this would be 2 cubed over, this is 3 factorial, 10 to the 7 times 7 plus, plug in n equals 2. So this is going to be 2 to the 5. 2n plus 1. So this is going to be 5 factorial. 10 to the 4 times 2 plus 3 times 11. And then minus dot, dot, dot. So approximating it with 2 fractions, I'll just use the first 2, right? So the integral from 1 to 1/10 of sine of 2x squared dx is approximately equal to these 2 fractions. 2 over 3 times 10 cubed minus 8 over 6 times 7 times 10 to the 7. And this is the approximation with 2 fractions. Okay. So you add these up, you'll actually get a number. So, I mean, do I want to do this? Let's actually work out what that is. This is just for curiosity. Like, you wouldn't need to do this. I'm not going to assume that you have a calculator. It's actually a very small number. It's actually 0.00066664761. I don't actually know if there are more digits to it, but that's the approximation I get. Right. So that's roughly the answer, at least with a 2 fraction approximation. Now, what is the last question? So it says here, you need not simplify your answer, whatever. Give an upper bound for the error in your estimate. So one thing you would want to notice is that the series that you have here is actually an alternating series because it has that -1 to the n in the answer. So we can actually use the alternating series approximation theorem. So upper bound on the error. Realize here is this is it's an alternating series. So therefore, I can use the alternating series approximation theorem by the alternating series approximation theorem. The error, which is just going to be S minus Sn, where Sn is the nth partial sum. And in this case, it's going to be less than or equal to, technically here it's A2, because n starts from 0 here. So here I'm writing S1, but this is actually the second partial sum. We started at n equals 0. And so A2 here, this is actually the third term. And we know an alternating series, wherever you stop the sum, the magnitude you are away from the actual answer is actually the magnitude of the very next term. So that's why I found the very next term. So even though they asked me for 2 fractions, I actually found 3 because I saw ahead of time that they're going to ask me when this thing actually approximate the error. And so I would be able to say this means an upper bound on the error is going to be this fraction. 32 over 5 factorial times 10 to the 11 times 11 is an upper bound on the error. Now, what is that actually? Take 32 divided by 5 factorial is 120 times 11. Times 10 to the 11. Ooh, that's actually pretty good. This here, we're actually off by, this is roughly, just for your information, like you won't have to actually know this because you wouldn't have a calculator. This is 2.4242 times 10 to the minus 13. So this is actually a very good approximation. Like we are going to be correct up to the first 13 digits up to the first 13 decimal points, right? So the actual answer is, what was this? 3, 6, 9, 11, 12. Like all of these will actually be the first 12 digits. Like those are exactly going to be the first 12 digits. Right? Isn't that crazy? Just 2 fractions gets me to close to the answer. It's the function, it's the fact that I have sine of something and the angle is squared, and I'm only not going that far. Like all those things contributing to getting me to a pretty accurate answer with just 2 fractions. Right? Like me as a lowly human, I could actually compute this integral, which is impossible to integrate, and I'm good up to 13 decimal places. So yeah, so that's how you would do this one. So this is a very important application. Being able to compute integrals and approximate them and figuring out how close are you to the actual answer. By the way, we know that the third term is positive. So that means that S minus Sn is positive, which means that the actual answer is larger than our answer. So the actual answer is going to be slightly bigger than our approximation. But it's only going to be bigger starting from the 13th decimal place. Like if your calculator has 10 decimal places, 10 digits, it's not going to know the difference. Right, so it's pretty cool, I'd say. Any questions on this problem? Okay. It's a very important problem type, so I have a second example that's very similar. Going to do essentially the same thing, but here we're using the integral from 0 to 1 of e to the minus x squared. So we're going to find a Maclaurin series for it. We are going to evaluate the integral. We're going to approximate it with the sum of two fractions. We're going to say how far away from the actual answer we are. And that's how we're going to continue. And again, remember e to the minus x squared, like that's, that doesn't have an elementary antiderivative. Like you wouldn't be able to think of a function where when you differentiate it, you would get e to the minus x squared as the answer. So if I ask you that to approximate the integral 0 to 1 and tell me how far off your approximation is if you use two fractions, you'd first start by finding a Maclaurin series for the e to the minus x squared. So we know e to the x is the sum n goes from 0 to infinity of x to the n over n factorial. And this means like e to the minus x squared is just going to be the sum and goes from 0 to infinity of minus x squared to the n over n factorial. So in other words, as a series, this is minus 1 to the n, x to the 2n over n factorial. B. Now we want to integrate 0 to 1 of e to the minus x squared. And by the way, remember e to the minus x squared is actually a very important function, like in statistics. Like if you wanted to find, like those of you who are taking statistics, you look up that table, you would have like a normal distribution table in like the back of your book. And it tells you like this, for each z-score, what is the area under the normal curve? It's actually integrating a function, not this function exactly, but very similar to this. It's actually 1 over the radical of 2 pi times e to the minus x squared over 2. And if you integrate this from 0 up to some z-score, it will actually tell you, you know, under your normal distribution, it will tell you the area under the normal curve. And so in a table, you'd have like some decimal digits in the back of your textbook telling you what that is. And of course, your teacher always tells you, oh, you can't actually just figure this out. You look it up in the table. Well, that table is actually giving you the value of this integral. And you're like, well, if we couldn't figure it out and we look up in the table, how did the people who wrote the table figure it out? This is how they figured it out. They did this integral. And they approximate it to within 4 decimal places and they put it in the table. So this integral is actually pretty important for other applications. So for statistics, probability, this is actually a very important type of integral. So it's not a completely random example, but it's a very simple function for which we know the antiderivative just as a nice function doesn't exist. You can't just plug it into your calculator and it'll be all fine. You have to go through some hoops. So here I would just replace this function with its power series from Maclaurin series. Because of absolute convergence, I can flip this, the series and the integral sign. Looks pretty scary, but x is the only variable here. Everyone else is a constant. So it actually just comes down to the power rule, because this is essentially an infinite polynomial. I'm differentiating it like I would any polynomial. We'll leave the coefficient alone, differentiate the x to the end part, integrate the x to the end part. So you add 1 to the power and you divide by the new power. And here, though, it's a definite integral, so we're going to plug that in. So the series of this expression is actually the antiderivative, the indefinite integral. But we want a definite integral, so we're going to apply the fundamental theorem of calculus. Obviously, if I plug in x equals 0, it wipes everything out. So we only have for x equals 1. So this would just be the series minus 1 to the n over n factorial times 2n plus 1. Now, what that is, so I would approximate this. I'm going to plug in n equals 0. I'm going to plug in n equals 1. That will give me the approximation for 2 terms. But I know it's an alternating series, and I'm going to want to judge how good these 2 terms are. So I would actually need a 3rd term. Because the very next term tells me how good the alternating series partial sum is. So if I plug in n equals 0, I would get minus 1 to the 0 over 0 factorial, which is 1, 2 to 0. So I just get 1 minus 1 over when n equals 1, I get 3 plus 1 over when n equals 2, 2 factorial. That's 2 times 5, that's 10 minus, I don't care. So this would mean that the integral from 0 to 1 of e to the minus x squared dx is roughly 1 minus a third. So this integral is roughly 2/3, 1.67 or something like that. C. Let's look, how far away is that from the answer? Upper bound on the error. By the alternating series approximation theorem. We know that the error is going to be less than or equal to the 3rd term. So that's actually 1 over 10. So I'm actually 0.1 away from the answer. So this should be roughly 0.567, something like that. Well, I don't know if it's actually positive. So S minus Sn is positive. So yeah, so the actual answer is should be a little bit bigger. So it's probably around 1.7. I don't know, would Wolfram alpha get me that? Yeah, roughly 1.746, blah, blah, blah. It's pretty good, right? Our guess would be 1.67. Like if you round it to 1 decimal place, it's, our guess would be 0.67. Round to 1 decimal place is 0.7. So we're actually correct up to the 1st decimal place. Yeah. So, and that's the farthest we can go. So we're off by at most 0.1, but it's probably actually a little bit less if you actually do the direct computation. I could actually also like a bonus. Like I could add another part to this question, and I could ask you something like, is our approximation larger or smaller than the actual answer? Right, like I could ask that. And the answer to that would be, well, S minus Sn has the same sign as the an term, an plus 1 term. So since A2 has a positive sign, this means that S minus Sn is positive. So this means S is larger than Sn. So the actual answer is larger than our, well, we can say our approximation is smaller because that's how the question was asked. So our approximation is smaller than the actual answer. By about 0.1. Which, I mean, doing this on a test, I wouldn't necessarily require that you point that out, but that could be an additional question that I could ask that I would expect you to know how to answer. So I figured, yeah. So for a problem like this, I think that's everything I would ask, could ask. So a problem like this is potentially a 4-step problem. This is everything. And maybe I might not even ask you separately to find the Maclaurin series using a known Maclaurin series or using a known power series, because that part I would think would be obvious based on the context of the question, the fact that you can't integrate it in terms of elementary functions, and the fact that I'm asking you to approximate it. But yeah, that's another one. So any questions on this problem type? Like I said, it's a very important problem type. It's the most important application for a series that we're going to be using. So generally speaking, like series, yeah, so series, there are like 2 big classes of problems that I'm going to ask you guys. I'm going to ask you to tell me whether or not a series converges. And I could ask you to tell me the kind of convergence, absolute versus conditional, or versus diverges, and use the series to approximate some integral. There's actually one I'm looking. So I can actually ask you both of these kinds of problems. But yeah, that's where we are. Now, what I want to do for the rest of class, it's kind of talking about some conceptual ideas. So it's not really something that you're going to have to do calculations about, but it's just things that you should know that I could ask you about. So I could ask you like some true or false questions or some multiple choice questions or select all apply questions based on what I'm going to be talking about. Because it's really a conceptual thing. So I've touched on the idea that sometimes you can create a Taylor series and it not actually be a good descriptor of your function, right? And also this can happen in all sorts of ways. So sometimes you can have a function, you create a Taylor series off that, based on that function using the mechanism that we did before, and the series matches the function. They're one and the same. You can think of one as being equivalent to the other. You can swap one out at will and nothing will be different. Like the series is the function. But there are times when this is not the case. So there are times when, for example, you can have a function, you can create a Taylor series, and that Taylor series actually describes another function, right? Or sometimes you can have a function but it actually doesn't even have a Taylor series. Like you actually can't construct the series because something breaks down. And the two main culprits for that would be either you can't differentiate the thing infinitely often, like there comes a point where your f to the n, the nth derivative is undefined, or the nth derivative grows too big in the sense that the coefficients get so big that once you try to force the series to converge, it doesn't converge. It will only converge at a single point, not on an interval, and then it's essentially useless, right? So when you plug it into the ratio test, you get that it diverges unless you just plug in and do like the center point. And so it only converges at a single point, which you can't do anything with that. Like you might as well just think of this thing as being a constant at a single point on the real line. Like it's not a bona fide function at that point anymore. There's only one possible input, one possible output. So all sorts of things like that could happen. So the question is, when do we have to worry about this? What do we have to actually think about? So that comes down to actually using Taylor's theorem. And Taylor's theorem tells us that if we can find up to n derivatives, we can describe a function like this on an interval a, b. So this is like if we're on the interval a, b. Right. By the way, you should notice, FYI, if we stop at f of b equals f of a plus f prime of a times x minus a, you get the tangent line approximation. So there are linear approximation. From Calc 1. But essentially, you can actually extend this idea to talk more generally about things. And you can extend this in terms of multiple derivatives. So so back in Calc 1, you learned that this is almost that, which is true. And you use that fact in Calc 1. But what is this exactly? And it turns out that's what it is exactly, right? To fill in all the terms to make the approximate equal sign in Calc 1 a bona fide equal sign, this would be the full formula. Okay, so that's the first thing. Another thing is that you can essentially get the mean value theorem here at a certain point. If you just pick a certain c in the interval, you can also derive the mean value theorem from this. So it's a pretty cool thing. And so you would get, the mean value theorem is saying this. There is some c for which this is exactly equal. That's also possible. Okay, so that's another thing. Another thing is that now you can write out a whole function in terms of this infinite expansion. And this is really like a Taylor series here. If you look at the formula, it's this guy where I'm just extending forever. But eventually I get to somewhere and I put the remainder term. So it's every term after this in the Taylor series. So the n plus first derivative, the n plus second derivative, the n plus third derivative, going on forever. So this is like a fully fleshed out Taylor series. But here we just stop it at the nth term and then continue. So this first part here is the nth degree Taylor polynomial. So it's just a partial sum of a Taylor series. Let me be specific, the nth partial sum of a Taylor series. And we mentioned that the remainder term is everything else. Now, it turns out that this is going to be true. I don't expect you to know why, but that is actually true. It's kind of true for the same reason over here. It's like a mean value theorem applied in a general sense. So we can pick a point C for which all the infinite number of terms afterwards can be approximated by that expression. And here, well, I was actually going to write out what this guy was, but I think you guys would be okay with it. I don't know, maybe I should do it here. So remember the Taylor series for f of x would actually look like the sum n goes from 0 to infinity of f to the nth derivative evaluated x naught over n factorial times x minus x naught to the n. And you can start writing that out like f of x naught plus f prime of x naught times x plus f double prime at x naught over 2 factorial times squared plus dot dot dot. You can keep going until you get to the nth derivative evaluated x naught over n factorial x minus x naught to the n. But of course, it goes on infinity, right? So there, you can keep going, you know, n plus first derivative over n plus 1 factorial times x minus x naught to the n plus 1 plus f to the n plus second derivative n plus second factorial x minus x naught to the n plus second plus da da da. Now this first part here is what I'm telling you about. It's the nth degree Taylor polynomial. This we would call Tn, nth degree Taylor polynomial. So that's a phrase that you'll hear me say. So I can mention this in a problem. Oh, blah, 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 consider the nth degree Taylor polynomial. This is what I'm talking about, this polynomial. Write out the Taylor series up to the power n. But of course, the Taylor series is an infinite series. So there's going to be an infinite number of terms left over. That is the R sub n, the remainder term, right? I think that notation is used later on. Okay, so here's the actual idea. If you can prove that the remainder term approaches 0 as n approaches infinity, for every x in the interval where that series converges, then equality will result. And you can replace that function with its Taylor series. So if you can prove that this infinite list of terms here, as n gets big, though that everything circled in red gets super small, it just becomes like a very, very small number. It goes to 0, in fact, then this is actually true. And so that will tell you that a Taylor series will converge. I don't know why it looks like that. I have to move that box down a little bit. So this gives you the conditions for which a Taylor series will exactly describe the function. If you, all this junk in red goes to 0 as n goes to infinity, then we're good. If it doesn't, then it doesn't. And we can actually use the previous two theorems to actually figure that out. We're really just looking at this expression and trying to see if it would go to 0. That can actually be summarized in this theorem right here, that the magnitude of your remainder term can be thought of as this expression, where the m describes an upper bound on your n plus first derivative. For example, for the sine function and the cosine function, m can be equal to 1, right? Because the nth derivative of sine is going to be at most 1, because the answer is either going to be a sine or a cosine. In magnitude, these never grow past 1. So you can imagine plugging a 1 into this formula and then taking the limit as n approaches infinity. What happens? It goes to 0. And that's what tells you that the sine and cosine would actually be exactly described by their Taylor polynomial. You can choose m equals e to the c, where c is the right side, the left interval endpoint, and prove that e to the x is exactly described by its Taylor polynomial. So you can actually do this, right? And I mentioned that here. And so that's when it actually goes correct. So this, I would say, this kind of summarizes all the idea. I would expect you to know this. Here, I would say you're not required to like know this in detail, but you just required to know the terms, not required to know in detail. Just the notation introduced, which I think is in further introduced. But I definitely expect you to know this idea. Know that the remainder term can be described by that, and know that if the remainder term approaches 0 as n approaches infinity, then your Taylor series and your function will be exactly the same thing. You can interchangeable. They're interchangeable. One can replace the other one. I have some examples here of when Taylor series goes wrong. A little bit of dramatic. But these are some examples of functions that they won't work out to have a Taylor series. I guess I can talk about them a little bit later on. But what I actually want to do is show you some cool animations from here. Just for you guys to see Taylor series in action and what they can do and how you'd actually go about approximating them. So let me... So I'm going to show you the first link, the fourth link, and the last link here. So hopefully you can see that. So for example, I can click on e to the x. This is, you can see the black here is the graph for e to the x. And the red curve is going to be the Taylor polynomial, but it has a finite number. This is, here it tells you the n value. So here we're at the 0 degree Taylor polynomial, which is just a horizontal line, right? Going through 1, right? The linear term of e to the x's Maclaurin series is just 1, right? Then it would go to 1 plus x, then 1 plus x squared over 2, then 1 plus x squared over 2 plus x cubed over 6, then blah, blah, blah. So you can actually see that this red curve, the higher up the power goes, the closer it's going to fit to this. And if you actually started graphing it, you'll realize that this black curve is going to be, the red curve is going to fit this black curve. So if you were to click play here, look at that. Isn't that beautiful? So the red curve at any given point is a finite degree polynomial going up to power 20, as you can see here. I can also do it for something like this. So at any given time, the red curve is a polynomial. Notice that it's an even degree polynomial. Both ends actually go up or down. And that's e to the minus x squared over 2. We actually know that. Here's a sine function. And you can see our polynomial starting to fit the sine function. So if you stop it at any finite point, the red curve doesn't fit the entire black curve. But that's the point. That's the point. Like as you go off to infinity, eventually it will fit everything. So in any finite window, it'll only fit a part of the curve up to a certain interval, but then the remainder term is the part that's off. And you can do this with even the logarithm, right? So we have the polynomial is getting closer and closer to the logarithm, which I think is cool. There were some other functions here, which you can see. And that number is telling you the power of the polynomial. That's another like interesting thing. I don't know if that actually shared. When I clicked on this, it had a pop-up. And the Wikipedia page, like it describes polynomials, and it also has some animations. Right, this was like n equals 2, n equals 3, n equals 4, n equals 5. And this looks like the e to the x as well. But this sort of tells you, like, if you take a finite number of terms, and oh, here they actually also expanded the sum under a radical. So this is where you can see that the coefficients are the ones that we had from before. And they still also use this this identity, the binomial theorem, binomial series, the generalized one. So yeah, it's all pretty cool stuff. And you can actually check out more of these. Yeah, you can check out more of those integrals, those animations. That's pretty much all we wanted to do with series, actually. So that last part there, it's more of a conceptual thing that I can quiz you on. In terms of what you need to be able to computationally do with series, you have to be able to prove that they converge, whether and prove that they converge to various degrees. So just like converge absolutely, or converge conditionally, or diverges. I also would expect you to know how to use series to evaluate integrals and interpret them. Some of maybe, I probably won't ask this directly, but maybe using series to compute limits or do some other interesting things I might ask you as a bonus problem or something like that. And conceptually, I might ask you about, oh, does this Taylor series describe this function, or under what conditions would a Taylor series describe its function? And I'll do some examples like that with you guys tomorrow, I guess. Like right now, we can wrap up. But series is pretty much done. Next, we're going to jump to chapter 10, I want to say. Like we're going to do parametric equations. So I think that's chapter 10. But yeah, we're pretty much done with everything we want to do from chapter 11. We're going to do chapter 10. And that's that. So that's all I want to do tonight. So I'm going to let you guys go. Have a good night. I will see you guys in the next one. Ciao.